Thanks very much. So in the next 15 minutes before the lunch break, I want to tell you about a project that we have been doing together at the Institute, in which we try to connect the formation of a planet to what we can actually see from the planet when it has formed. And I am a collaborator in this project. It was actually led by Christoph Mordesini, but I'm the only one here from this group, so I get to talk about it. And I want to quickly, but that was luckily already done a little bit, or actually quite extensively by the earlier speakers, remind you if you want to try and connect the composition of the planet to how it formed. First, how do we find out what the composition of a planet is? And there are a couple of ways that we can use from observations. And one is to measure the mass and the radius of a planet. And combining these, we can get an estimate for the mean density of the planet. And this can give us an idea about the bulk enrichment of the planet, although there are some degeneracies in that as well. If we actually want to measure if an individual molecule is actually present in the atmosphere, we go to spectra, and we've also talked about these today: transmission spectra, emission spectra. If the planet has a large enough angular separation from the host star, we can also use direct imaging spectra. And yeah, from that we can get individual molecular abundances and an idea about the composition of the atmosphere. Right. So I have also bad news for you, because unfortunately the first project that we tried to tackle with this was the formation of hot Jupiters, which I think are pretty deadly to life, but I hope it's still interesting to you. So what we looked at in terms of hot Jupiter formation, something that is known because hot Jupiters are gas planets that are quite close to their star, 0.03, 0.05 AU. One finds it's pretty hard to form them so close to their stars. So they must have formed somewhere else. And what's an interesting question is, how do you bring a planet that has formed further outside in the disk close enough to the star to end up as a hot Jupiter? And you can think of at least two groups of methods. One is the so-called disk migration, when the planet forms somewhere in the disk and then gravitationally interacts with the disk material, exchanges angular momentum, and moves in close to the star. And obviously, for this to work, you need to have the disk present when you migrate. The other method is, there are multiple methods that you can use, or ways that you can think about to bring a planet close in. Is planet-planet scattering, or Kozai-Lidov oscillations, where the planet, after the disk has dispersed, gravitationally interacts with other planets or with a companion to the host star a little bit further out, which can scatter the planet, give it a high eccentricity, and when the planet passes then close to its star during periastron passage, tidal forces will actually circularize the planetary orbit, and then you end up with a hot Jupiter. And so the idea would be to find, actually, can we know from looking at the composition of a planet if a planet has formed in the outer parts of the disk or in the inner parts of the disk? Because if you find a hot Jupiter that must have formed in the outer parts of the disk, then disk migration is an unlikely scenario, because if disk migration is the scenario that occurred, then the planet would have migrated through the inner disk and accreted material. So to tackle this project, we constructed something that we call the chain project. Chain because we have a chain of model links that actually connect the formation of the planet to the observable spectrum. So I'll go through the links now. The first link is the planet formation and evolution link. There we use a core accretion approach. We have disk evolution, orbital migration, and so on. So this is maybe I don't know if you know Chris Mordesini. This is also known a little bit as the Bern model. So the planetary formation evolution model tells us at which time, at which position of the disk did we accrete how much gas, how many planetesimals. And now we have to make assumptions about the composition of the volatile gas and the planetesimals and the refractory component. And we can play around with different setups for the composition of these accretable material. So the next chain link is the atmospheric model, and that's where I come in. So I'm the group's atmosphere guy. And we use the mass, radius, elemental compositions, distance to the star, internal temperature, all these things, give that to the atmospheric model, and this calculates self-consistent atmospheric structures, molecular abundance profiles, emission and transmission spectra. So from that we get an observable spectrum from the formation of the planet. And in order to actually get an observation, the last link is to carry out synthetic observations using a radiometric model. And whatever, well, we can in principle simulate whichever telescope we want as long as we have some parameters to describe it. And this completes the chain, and the first paper about this is out, so if you want to give it a look, you can find it here. And also, many speakers showed a picture of their group, or the group that they're working in at some point, so I also want to do that. So this is the chain gang. And these are the 5 authors. This is Chris Marazzini, who was the first author. And I think it's actually a good thing as a PhD student to have your advisors chained to you, because you can always ask them questions and they can't run away. Right. So let's look at some results that we found. So one thing that we found from the synthetic planet populations, and you can also see that from actual observations of planets, is that the planetary bulk enrichment is dominated by the planetesimal accretion. It's not the disk gas which sets the total enrichment of the planet, at least if it's below 2 to 10 Jupiter masses. It's the accretion of planetesimals that enriches the planetary envelope. And having that in mind, we asked ourselves, well, if you want to constrain where the planet forms in the disk, what are the 2 most fundamentally different ways of how to form a planet? And we came up with 2 pretty straightforward planets. The one was called the dry planet, one was called the wet planet, and if you see the protoplanetary disk from the side, the dry planet is a planet that forms inside the ice line in the protoplanetary disk. And that's why it's called dry, because the planetesimals do not have any water or volatile ices in them. The wet planet forms outside the water ice line, and there's water in the planetesimals, and that's why it's called wet. And something that was actually quite important and interesting is that it's important to know how much organic carbon you put into the refractory material that the dry planet accretes. And you will see why that is in some minutes. How do the results look like in terms of composition for these 2 planets? These numbers do not add up to 100% because they're in units of Earth masses, just in case you're wondering. So this is the composition of the dry planet, this of the wet planet. Both are dominated by hydrogen and helium. And this is the core mass in black. And the dry planet actually accreted 21 Earth masses in refractories, whereas the wet planet accreted a little bit of refractories, but also a lot of volatile ices. And has in total a higher enrichment than the dry planet has. Coming back to this carbon depletion, sorry, I already said it now, to the carbon abundance that we assume for the dry planet. So when we saw how sensitive our results are to the organic carbon content of the refractories, we looked at what we should assume for the carbon content of the planetesimals. And then when we looked at it, we found that apparently the inner solar system is quite strongly depleted in carbon in the solids. So we looked a little bit in the literature, and what you find is if you look at comets that originate somewhere in the outer parts, you find that the carbon abundance is roughly similar to what you find in the ISM. But when you go further inside, if you look at asteroids and if you look at chondrites, so carbonaceous chondrites, ordinary chondrites, ancestite chondrites, which are supposed to form increasingly further in, you find that these are increasingly stronger, increasingly more strongly depleted in carbon. And finally, if you look at Earth, Earth is actually quite strongly depleted in carbon. Most of the carbon is locked up on the surface, basically. That's why we still have life on Earth, basically. So we were quite surprised, also we didn't know when we set out to do this project. And so we assume this black line here actually as our carbon depletion model for the planets. So what do we get for typical cases of the wet and dry planet? So the blue histograms show the abundances in the planets for the wet planet. Red is the dry planet with carbon depletion, and light red is the dry planet when we turn off carbon depletion. And I want to focus on the oxygen, carbon to oxygen number ratio, because this is an important parameter and sets the spectral appearance of a planet. If you have more carbon than oxygen in the atmosphere, you'll have strong methane features. If you have more oxygen, you will have strong water features. What we find in our nominal model is that both wet and dry planets are oxygen rich. And this was kind of disappointing to us, because if it had been otherwise, if you wouldn't have the carbon depletion, it might be the other way around. So we don't get an easy switch for a planet which formed either inside or outside the ice line in the disk. What we find is for the dry planet, so the red bars here, is the C/O ratio is below 0.2 because of the strong carbon depletion in the inner disk. And for the wet planet, it ranges between 0.1 and 0.5. And this range actually comes, which basically vary the height of this bar, comes from our, not sufficient knowledge of how efficiently you trap other volatile species into water ices when the water condenses in the outer parts of the disk, which is called clathrate formation. Right. So if we knew that better, if we could put a better estimate on the C/O ratio of the wet planet, C/O ratios in the range of 0.1, 0.2 in difference are still may still be retrievable by spectral observations, then we might have some handle on assessing where the planet forms. But right now, we need to know more about the chemistry in order to do that. Right. So how do the spectra look like for these planets? So wet planet, dry planet, they look a little quite different actually, but that is not so much to do with the composition, but more with the total enrichment. The dry planet is less strongly enriched. The photosphere goes to lower pressures, and then it just looks, the spectrum looks different. The amplitude of the features becomes smaller, but they both put out the same amount of energy. And they're both dominated by water features. You see that here. If we had a dry planet without carbon depletion, then it would look like this. And then instead of the water features, you would get strong methane features, which would have been the nice case, but unfortunately we think that this is unlikely. Also to show you how the last link in the chain functions, these are synthetic observations for JWST for one transit. For three instrument channels, so in total for every planet you would have to take 3 transit eclipse observations to get such an emission spectrum. But it shows you the expected data quality of JWST, and that if we know more about the planetary formation, we might actually be able to say something about where the planets formed. Right. To conclude, so I talked about the chain model and that we can try to connect the formation of a planet to spectra. Something that we found out and is also already part partially in literature, also for observations, is that really planetary enrichment should be dominated by planetesimal accretion. We weren't so fully aware of that when we started. The inner solar system seems to be strongly depleted in carbon, and therefore, because most hot Jupiters have masses below 2 Jupiter masses, we expect that most hot Jupiters are oxygen-rich. And we might be able to retrieve C2O ratios between planets that formed inside the ice line or outside the ice line. But in order to know which values we have to connect to the formation location for the wet planet, we have to know more about the disk chemistry. Thanks very much.